Hello and good afternoon. My name is Hassan Imran and I am currently studying Masters in Software Systems Engineering. Today I will be presenting my master's thesis. The topic is Model Updating Digital Twins and it is about updating SysML models for a cyber physical production system using digital twins. Why do we need a model updating digital twin? So we need to monitor changes in efficiency and performance of cyber physical production systems. There's also we need to determine deviations between the as operated and the as designed system behavior. Um, then it is also there's a need of having models available which reflect the as running state of the system. So we already have models for the design time, but we would also like to have models which show the running state of the system. And this is because sometimes the models of design time do not hold because of the wear and tear of the system. So there can be deviations between the as running and the as design time models, and we would like to capture those. For this, we will present a case study for the injection molding process and how having a model updating digital twin would help improve this. So some of the problems that can occur during the injection molding process are that we can have warping, we can have flow lines and burn marks on the mold. We could have air pockets or vacuums inside them, and as shown in these pictures, this is a vacuum void, so there's air gaps inside the mold. This is warping, with it means that the shape is bent. These are like lines appearing on the mold, and these are burn marks, so we want to avoid them, and these can easily be avoided by adjusting the following factors in the mold: so the flow rate, the temperature and pressure. And if we have a digital twin for this, it is very easy to adjust these in the digital twin, and then they would be changed in the cyber physical production system. We chose this case study because it is very easy to change these in the digital twins, and they also have values which are predefined in the design time models. So if the digital twin has wear and tear, so there can be a deviation between the running system and the design time models, and we would like to capture these, and we would like to update the models to reflect the as running behavior for this. So what are the requirements for developing a model updating digital twin? So I think the first requirement is that we have to have the engineering models available. Then we have to have information regarding which values do we need to monitor for the digital twin. Then we would also need to add a module inside the digital twin which supports the updating of models. And then we would have to have we would need a mechanism which actually updates the design time models, which takes the design time models as input and produces updated models for the injection molding machine. Then we also need to store them once they are updated, and then we have to notify the cyber physical production system that an updated model is available. This would then mean that it could be an indication to the development team that when you're planning for the next cycle or the next phase, you can refer to the newer models. So how do the engineering models of a digital twin look like? So we are considering SysML v2 models. So so here you can see that this is a block definition diagram. So it is a injection molding machine. It has a block called my RBUG instance, and it has two sub blocks. We can call them parts. So there are the plasticizing unit and the clamping tool. So for the plasticizing unit, we have two values called the temperature and the left temperature. Both are of type integer and they have a predefined value. So this is the design time model of the digital twin. And we have two assumptions here: that the model are made as SysML models and that they are stored in memory. So we choose the in-memory option for the digital twin because this is the fastest way to retrieve the model when we need to update it. Then we also have to have information regarding which variables need to be monitored. So for that, we have developed a tagging table for the SysML language. So the tagging table basically represents the language elements of the SysML language. So we can easily see which elements or we can observe or update. So what do the tags mean? Observable and updatable. So here we have defined an updatable as the value which can be updated or changed in the model when we create a new one. And observable here means that we can log the value, but we cannot update the value in the design time model. Um, Using the tagging table, we then define a tag model. So we can get, so looking at the BBD, we can see that which values are type of attribute or a port or with the default value, and then we can create tags for it. So for example, we can create a tag for the myRBUG instance and the plasticizing unit, and then we can put them as observable or updatable. Now, one thing to note here is that all values are that are updatable are also observable, but not the other way around. Once we know which values we need to monitor, then we can work on developing a model update module for the digital twin. So we already have a digital twin architecture diagram available, and so we have to make architectural changes and methodical changes. So for the architectural changes, we have to add support for in the data processor for retrieving values which are defined in the tag model. In the evaluator, we need to define model updating events which will be used. In the reasoner, we introduce a new component called the model update reasoner, which takes in the goals which are categorized as model update goals. And in the executor, we have the model updater, which takes in solutions which are of type model update. And in the methodical changes, we add support for the SysML v2 models in the digital twin architecture, and in the digital twin event language, we add support for model update events. So here is the diagram for the digital twin, and here is the model updating digital twin. So as you can see here, we have the goal dispatcher and the solution merger, and similarly we have a solution dispatcher in the execute. And here you can see that in the reasoner you can have multiple update um, multiple reasoner components based on the application, and the same goes for the executor. So the dispatcher would filter these goals depending on the type, and it would then pass it to the to the corresponding component in the reasoner, and then you would create a solution. This would be discussed in detail in the next slides. So modifying the digital twin event language. We talked about the how the data processor would then need to be changed to also, it would actually just need support for taking values which are defined in the tag model, but the event language is the one that will create new events called the model update event. So here you can see that we have an example of a model update event. It is, we call it the event temperature greater than 0. So it has an event and an action and a rule. So the is event tells you which attribute you need to get from the data processor, and then it checks if the event will trigger or not. So it would check the value at its current state, and it would see if it is greater than 7.5. If if it is true, then the corresponding action will take place, and you would then create an update model goal for it. This basically means that the rule that this event is mapped to this action. So whenever this event occurs, this action would be triggered. Similarly, we have a model update goal class which extends the goal. So whenever this event is triggered, this goal would be created, and then this would be passed to the reasoner. So it would have the attribute value, and the model FQN, and a fully qualified name, and it would also have um, the digital shadow, which is part of the goal class. How an event model works. So at first we create we create we have an initialization function which creates a new event. Then we have a new update. We create a new action, and then we generate a new rule, and the event registry then registers this rule. And what happens when an event is executed? So the event controller, the execute event is called on the event controller. It returns the list of events. All of the events are run and they are checked. Sorry. And then if an event is true, then the corresponding actions are generated, and then the action is performed according to this. Now we talk about the reasoner. So as we talked about that there are new components introduced. So what the reasoner would do is, from the evaluator, it would then get the corresponding type of goal. Based on the goal dispatcher would filter it and pass it to the respective component. For in this example, we only talk about the model update goal. So the model update goal will be passed to the model update reasoner. It would be then transformed to a solution, and then it would be passed to the solution merger, which would then be sent to the executor. Um, in the executor, we have the list of solutions. Again, we would have a model update solution, which the solution dispatcher would filter and send to the model manager. So here it would be passed to the model updater, and the model updater would then update the model. It would create a new model from the design time model, and it would then store it in the data lake, and it would also send a model changed action event to the model change notifier, which would basically then notify the system that the design time model has been updated and a newer model is available. This is the activity diagram which shows the creation of a model updating digital twin. So here, firstly, you have to have the domain models and the SysML v2 models. Once you have these two, you then create Monty-Arc models using the domain models and the SysML models, and you create the tagging models using the domain models and the SysML v2 models. So the Monty-Arc models would then be used to generate code um, for the digital twin. It would also require the domain models for this, and the tagging models would be used to create the events. So the events would use the tag models, the domain models, and the SysML Me2 models. You would, for now, you have to handwrite the events using the tagging models. The tagging models are also handcrafted. Um, you have to define which attribute you need to monitor. You have to specify the condition on which the event is triggered. You have to define, if an event is triggered, what action needs to be taken, and you need to map the action. You need to map the events to the actions. And these event models are also passed to the generator, which then generates code for all of these. You get Java code from it, and then you can also use your own handwritten code to further enhance the behavior of the implementation files for the components of the digital twin. This is how the whole model updating digital twin architecture looks like once it has been generated. So the data processor has the data processor logic and the adapter. The adapter is basically the communication between the data lake and the digital twin. The data processor logic actually takes input the data query that it gets from the evaluator. It sees, it also then creates a data query which is then sent to the data adapter, which gets data from the data lake, and then the data processor logic sends a digital shadow as a response to the evaluator, which is then used to create the goal. In the reasoner, you have the goal dispatcher as talked about. It filters the goals, it then sends it to the respective components, and then you get the solution. So the reasoner then forwards the solutions to the executor. The executor filters the solutions based on the type and gives it to the corresponding application. And then then for example here for the model manager application, it just sends a notification to the CPSs about the change, and also it sends data to the data lake for storing the new model. um, yeah. Then storing the updated model to the data storage. So once have, what we do is, once we want to update it, we create a new SysML model and we store the updated model in the data lake. So this is the original design time model of our example. So we have the same RBurg instance and we have the temperature and the left temperature. And for that we create a tag model. So the tag model then defines it as observable and updatable. And then we have the event language. So the behavior checks for the temperature, and it then so it has an event. If the temperature is greater than 0, then the action would be triggered, and then this maps the event to the action. So if this is true, then we can see that a new model would be generated, which would then have an updated value which it got from the data lake. This would be the current value that it gets from the data lake, and it would create a new model and save that. We can now talk about some of the work that we can enhance in the thesis. So we can use the tag models to generate event models automatically. For now, we use the tag models to generate event model. We handcraft the event models again, and we can also add support for changing the type of attributes in the design time model. So for example, if we had an integer initially, then if you're creating a new block diagram, then we don't want the integer, but we instead want it to be as a double or a float value. Then we can add support for this. We then have to also define context conditions to evaluate if the updated model conforms to the original model. So once we change the type of attributes, we need to make sure that it does not it also has to conform to the original model. Then we can also add support for updating multiple values of the model at the same time. So in the executor, you have the design time model, and you can now update multiple values of the design time model in one cycle of the digital twin. And then you can update the runtime models. So every time, this would mean that every time you are using the latest runtime model of the digital twin and updating that one. So right now what happens is that you always use the design time model, the original model, and you update that and create iteration new versions using that model. But here we can also use the last created model for updating the models in the digital twin. Um, just to summarize, we talked about model updating digital twin infrastructure, which supports updating SysML v2 models. We talked about how the components can now handle different applications. So it's just not specific to one application now, but because of the approach of the infrastructure, you can now have multiple applications running in the same digital twin. And we also added specific goals and solutions. So the evaluator now, after once an event is triggered, it creates not a general goal, but a specific goal of a type of corresponding to an application. We also created model updating events using the digital twin event language. And as a proof of concept, we implemented a digital twin for updating models for the injection molding machine.